will be graded for sure, probably by the end of tomorrow, and then I'll have them back to you on Tuesday. Okay, so we're going back to circular motion. Yes. Okay, that's a good question. Next week, we will have a lab, and I will come up with some kind of small grade incentive for you to go because I've lost all my leverage now that the lab exams are done. But all it's going to be is the post-test of that intuition test that you took at the beginning. So it'll be quick again. What? You don't have to take it, but like I said, I'll give you a point or two on a test or something like that. I'll have to think about it, but just to try to get you there because it's good for me to have you take it, 5, well, yes, 5 points extra credit, but I haven't decided yet how much 5 points weighs into the class. So 5 points on a test seems a little excessive to me. We're going to have to agree to disagree on that one, I guess. I don't think so. Okay, so back to circular motion. So we did an example. We did the airplane example last time. Let's do an example now of non-uniform circular motion. So ooh, that's a good hand. I dare you to try to draw it as good as me. Okay, so let's say that there's a ball in a string being swung around in a circle. That's true. Depends how heavy the ball is, how sharp it is. And the idea is that this is up, so the weight is acting down towards the bottom of the page. The mass of the ball is 0.1 kilograms. And we're going to analyze the ball's motion at this point right here. So this is the point P that we care about. The cable, the string, has a length of 0.3 meters. And the speed of the ball at that instant so the speed of the ball at P is 10 meters per second. And at P, it's slowing down. It's on its way up, so it's slowing down at a rate of 9.81 meters per second squared. Okay, so that's the way it has to be. It turns out that the acceleration, the parallel part of the acceleration, has to be the free fall acceleration just right at that instant. Nowhere else, but that's right where its acceleration is free fall. And we want to calculate the tension in the string at that point. Okay, so let's try to make a little intuitive sense out of how this would work. If you're spinning ball in a string like this, it's always going to be speeding up when it goes down, and it's going to be slowing down when it goes up. So at the bottom, it's going to be at its fastest. At the top, it's going to be at its slowest. And the point that we're considering is somewhere in the middle. Where do you think the tension in the string is greatest and lowest? The bottom is where that string would be most likely to break. That's where the tension, the force requirement is the biggest. It's going to be the lowest at the top. And so again, that the tension of the string is going to be somewhere in the middle where we're analyzing it. And then what do you think generally would happen to the tension if you increase the speed that you're moving it? If it went from 10 meters per second to 20 meters per second, would the tension increase or decrease? Increase, and if you slow it down, the tension will decrease. Okay, so that's sort of how this works. And let's go through this calculation. So the first step is choose a view of this setup where you can see the path of the object as a circular shape. So the view that I drew is the view that we want to take to do the problem. Okay, so there's the path. And I'll put the coordinate system here, X and Y. And now the point that we want to analyze, it's given for us in this problem. Sometimes we get to choose, but we want to analyze that point there. The next step is to draw a vector from the point that you care about towards the center. That's the centripetal acceleration. And what do we know about the centripetal acceleration? Well, this is pointing, it's parallel to the x-axis. Is that vector in the positive or negative x direction? Negative, so centripetal acceleration is negative v squared over r for the x component, 0 for the y component. And we know v is 10 meters per second, and we know r is 0.3. So 10 squared is 100, divided by 0.3 is 333 and a third. And so this is negative 333.3 repeating 0. The last example problem we did, the speed was constant. It was uniform circular motion. So there was no tangential acceleration. This one, it says in the problem that it's slowing down. And so now we have to consider the tangential acceleration because the speed is changing. The ball is moving this way. So let's start by drawing the velocity vector. What's the direction of the velocity vector at this point? Up, yep. And it's slowing down, so what's the direction of the tangential acceleration? Down, opposite the velocity. So this is the tangential acceleration. If we didn't know anything about any numbers or anything, just based on the fact that it's moving in a circle and it's moving this way and slowing down, we could say we know that the total acceleration is somewhere in between those two directions. That's the stuff we do in lab. But we're going to be able to just come up with numbers for it now because we have enough to do all these calculations. So the tangential acceleration, is that in the positive y or negative y direction? Negative, so the tangential acceleration is 0x, negative y component, and it says that the magnitude of that has to be 8. No, it doesn't. It says it has to be negative 9.81, right? Because it says the rate that it's slowing down is 9.81. Okay, so what's the total acceleration vector? Yep, just those two vectors added together. So negative 333.3 repeating for x and negative 9.81 for y. And now that we know everything about the acceleration vector, now we can start trying to do calculations involving the forces. So free body diagram of the ball. There's a weight force acting down. It's equal to the mass times 9.81. So the mass is 0.1 kilograms. That means the weight force is 0.981 newtons. And then what direction does, well, so what other things are making contact with the boundary? The string, and what direction does that string force point? Yep, away from the body, parallel to the string, so like this. That's everything. So now Newton's second law says, well, this is in the negative x direction, so that cable force is negative T0. The weight force is 0, negative 0.981. And that's equal to the mass times the acceleration we just calculated. And now we can just look and see what we need. What we're looking for is this value t. That's what we're asked for. The y equation doesn't help us find t, so we can skip that one. It turns out it just says negative 0.981 is equal to negative 0.981, so that's encouraging. So the x equation says negative t plus 0 is equal to 0.1 times this, so it's equal to negative 33.3 repeating times the 0.1, yep. And so then t is equal to positive 33.3 repeating newtons. Yeah, well, if we were asked for the force vector that the cable applies to the ball, you would plug it in. The way I asked this question is just what's the tension, so that number is enough by itself. Okay, so if we increase the speed that we're spinning this around, that force would get bigger. If we decrease, that speed would get smaller. Any questions about that problem? Yes. Like for every problem like that? I think it is, so I would say like if your goal was just to get the right answer on a timed exam or something, like you're always like looking for those shortcuts. But on the exams I give, you always have plenty of time. And I think that it really solidifies this stuff to just keep going through all the steps all the same every time. So I would recommend not taking those shortcuts, but you're right that they're there. And like if you take, when you're taking like MCATs or, achievement tests or whatever, like for, it doesn't make sense to me, but they really want to see you figure out all those shortcuts or whatever. I don't really like that. So I say take the long way. Yeah, right. But I mean, they could just give you more time or fewer problems, but they don't ask me my opinion. Um, okay, so the set of steps that I've given you apply to every kind of circular motion problem except one. Anybody remember what the one kind of circular motion problems is that tetherball? Polar bear, did you say? Oh, okay. Um, so now we just have to learn one specific approach that we're only going to use for these tetherball kind of problems. So the one kind of circular motion problem we haven't addressed yet, haven't done yet, and that's tetherball problems. And a tetherball problem is one where a mass is moving in a circle that's parallel to the ground. And it's supported only by some kind of cable. Okay, so it's spinning around in a circle that's parallel to the floor. And the only thing supporting it, it can't be like rolling on the ground or anything. It's just hanging from a cable as it goes. So some examples of this are, one good example is the ball in a tetherball game. Yeah, it's a weird coincidence. I don't know, they're probably too dangerous somehow. But it can apply to any situation where you have something rotating in a horizontal circle connected only to a cable. So like an example would be like if you had like a car that was connected to a chain being held in the beak of like some kind of giant eagle. Okay, so as long as this car is moving in a circular path, it's horizontal, and it's only supported by a cable, that's a tetherball problem. Okay. No, that's a good question. So actually, a tetherball is not a perfect example of a tetherball problem. We're imagining that this ball is that it's on a hinge up above, and it just keeps. Yeah, like if a ceiling fan that's no, not a. I guess not because it's not connected to a cable. You know. Um, okay, so in problems like this, we're going to choose a different view than we do in every other kind of problem. We're going to choose a side view, and that means we won't be able to see the path as a circle. So the path won't appear to us as a circle. It will look like a line. Okay, so let me draw this. So if you're taking a side view of a tetherball problem, The circular path is just going to look like this. Anyone have any questions about that? Does that make sense? So if you were looking from above, you would see a circle. But just looking from the side, you just see the side of the circle, and it looks like the ball's just going back and forth. You know what I mean? Right. Yeah, like a funny pendulum because of the way the speed would change. But yes, it would look sort of like a pendulum. Now, the radius of the circle, remember the radius of the circle is important for calculating the centripetal acceleration. So where does the radius of the circle appear on this? From the center here to, yep, so this here is the radius. Okay. And if this, I'll call that L, the length of the string. If that's L, and this angle is theta, notice that the radius is always going to be the length times the cosine of that angle. Any questions about that? Making sense out of that? Okay, so once you've chosen this view, and we'll put the coordinate system like this. Now the rest of the steps are the same. Start with drawing the centripetal acceleration, calculate that. What about speed changes? So this is something important to keep in mind with these kind of problems. So notice. Tetherball problems. So, and I'll say, all of these problems that we're doing are idealized problems. Notice we're never talking about air resistance or any kind of friction. So these idealized tetherball problems that we're doing always uniform circular motion. And what do we know about the tangential acceleration in uniform circular motion? It's zero. So the tangential acceleration in tetherball problems is always zero. The speed's constant. Okay, let's do an example. Yeah, right. If, like, from experience with, living in the world, that if you got a ball spinning like that, it would be slowing down a little bit the whole time, and eventually it would stop. That's just the result of friction and stuff. And so since we're ignoring that, we don't have any way to include that in our calculations. There's no possible way to do that except friction. Yep. Because of the kind of force that cable applies. Okay, so let's say that We have a mass hanging from a cable, and the angle between the string and the horizontal is 45 degrees. And let's say that the length of the cable is 0.25 meters. And the mass of the ball is 1 kilogram. And we want to know two things. What are the cable tension and the speed of the ball? Okay, let's think for a second before we do the calculations, just intuitively about how these three things relate to each other. So as that string gets more horizontal, okay, so say that this angle wasn't 45 degrees, it was 10 degrees, and the ball was up here somewhere spinning around. What do you think would have to happen to the speed of the ball for that to be possible? It would have to increase. Can you imagine that? Like if you start out with something hanging from a string at a really slow speed, it's just going to be sort of dribbling around the bottom. And that angle would be a really big angle, close to 90 degrees. And if you speed it up a little, that angle is going to get smaller, and the ball is going to move away from the pole. And if you speed it up more, it'll eventually get to 45 degrees. And as you go faster and faster, it'll eventually, it'll get closer and closer to horizontal. By the way, it never can get to horizontal. It would take infinite speed to get horizontal. And as the speed is increasing, yes?
And this is assuming without any, like propeller blades, don't they?
Oh, yes. So this is assuming that there's no lift or anything like that. Air resistance, like just pure air resistance, doesn't affect that. But yeah, you can make the shape of things such that it'll get lift, and that, yeah. And so as that thing gets more and more horizontal, you're speeding it up. So as it speeds up, what would also happen to the tension in the cable? The tension would have to increase too. So the lowest tension you can have is when this is close to 90 degrees and just barely moving around the outside. And the tension gets higher as you speed it up, and as you speed it up, that angle gets smaller and approaches zero. Any questions about that? Okay, so let's take this view to do the problem. So we have a triangle like this. This angle is 45 degrees. I'll put the coordinate system here with its origin at the center of the circle. And now we can just start by drawing the centripetal acceleration. So the centripetal acceleration goes from the ball toward the center of the circle. Is that in the positive or negative x direction? Okay, so the centripetal acceleration, we know that it's positive v squared over r and 0 for y. We know that r is equal to the length of the string, 0.25, times the cosine of 45. And that is 0.1767, I think. So we can put this value in for r. We don't know what v is. We're trying to calculate that. So this is v squared over 0.1768, and then 0 for y. What about the tangential acceleration? It's 0 in every one of these kind of problems. So the total acceleration is v squared over 0.1768, 0 for y, plus the tangential, which is 0, because it's uniform circular motion. What's the next step? Yep. So free body diagram of the ball. So here's the ball. The weight's acting this way. That's 0.1 times 9.81, so 0.981. And then the cable force is away from the ball, parallel to the cable, so this way. And it has a magnitude of T. Okay, so now we have to think about what the components are of that cable force. So if this is our coordinate system, we'll put the tail of the vector at the origin, and its magnitude is T. This angle is 45 degrees. And so how would you represent the components of that force vector? Yeah, T times cosine and sine. Yep, so that force vector is going to be T times cosine of 45, T times sine of 45. So that's 0.7071 T, 0.7071 T. And now we can go to Newton's second law. We have the downward force of 0.981, so 0, negative 0.981, plus the cable force, 0.7071 T, 0.7071 T. And that's equal to the mass times the acceleration that we know. Well, we don't know v yet, but once we know v, we'll know it completely. So v squared over 0.1768, and then 0 for y. And what we're trying to solve for is t and v. We can use the y equation first to solve for t. So that says negative 0.981 plus 0.7071 t is equal to 0. And then plug that into the x equation, and you get, oh, I didn't solve it yet. Okay, so t then is equal to 0.981 divided by 0.7071. Can someone divide that? It's like 1.3 something. 387? 1.387 newtons. And now plug that into the x equation, and you get 0.7071 times t, which we now know is 1.387, is equal to whatever. What's 0.1 divided by 0.1768? 0.1 divided by 0.1768? 0.566 v squared. And so what do you get for v squared? Uh, that's the final one, right? 1.32 meters per second. Is that right? And so v, I think you divided the wrong way. 1.73. Okay. And then take the square root. You get a positive or negative. We want the positive. So the cable tension is 1.387 newtons, and the speed is 1.32 meters per second. If that angle is smaller, that would mean that it's closer to horizontal, and your tension would increase and your speed would increase. If that angle was bigger, it would mean it was the rope was closer to vertical, and that would mean that the speed and the tension both got smaller. Let me do this same problem one more time, but do it on the other side of the pole so you can see how the directions of everything work out if you do it on the left side. No, the right side, stage left. So I'm going to do it again, but this time using the view where the ball's here. This angle is 45. The coordinate system is here. Okay, so the signs of some things are going to change, but it's all going to work out, and in the end, our t and our speed will be the same. You can sort of, if you think about it, it sort of has to be the case because all we're doing is moving to the other, like moving around and looking at it from the other side. We're not changing anything about it. Okay, so now that we have the view, the first step is to draw a centripetal acceleration vector. Is that vector in the positive or negative x direction? Negative this time. It was in the positive last time. So the centripetal acceleration this time is negative v squared over r for x, and then 0 for y. And again, we know r. R is the same as it was in the first problem, so that's negative v squared over, what was it? 0.1768, and then 0 for y. And what's the tangential acceleration? Yep, that's always true in any tetherball problem. And so the total acceleration is negative v squared over 0.1768, and then 0 for y. So we have a negative now that we didn't have before. But in order for this to work out, that has to be countered by another negative that we have somewhere that we didn't before. So we'll see that happens too, and we'll end up with the same answers. So now we'll do a free body diagram of the ball. No. Ah. Oh no, I'm going to be so sad if it doesn't find it. Yes. Okay, so what did we lose? Oh man, we lost a lot. Well, okay, so this is the centripetal acceleration. And the centripetal acceleration vector is negative v squared over 0.1768, 0 for y. Uniform circular motion, so there's no tangential acceleration. So the total acceleration is negative v squared over 0.1768, 0 for y. And then a free body diagram of the ball. There's a weight force down of 0.981. There's a cable force that's this way this time, and it has a magnitude of t. And so now let's think about the components of this. Well, the magnitude is positive. A negative is just a direction. So it's a magnitude of 0.981 in the negative y direction, so the y component is negative. All right, so here's our coordinate system. There's the force. We know that this angle is 45 degrees. The magnitude of this is t. And so what's the angle theta for this vector? 135. So the force is t times cosine of 135, t times sine of 135, and that gives negative 0.7071 t for the x component, positive 0.7071 t for the y component. And that's the negative on the x component is the other negative that's going to cancel our first negative from before. And so now Newton's second law says 0, negative 0.981 plus negative 0.7071 t, positive 0.7071 t is equal to the mass times the acceleration, which is negative v squared over 0.1768, and then 0 for y. And now solving it, we'll go through just the same order we did before. The y equation says negative 0.981 plus 0.7071 t is equal to 0. And tell me what that is again, the tension value. 1.387 newtons, so that's our first answer. And then plug that into the x equation. And you get negative 0.7071 times 1.387 is equal to negative 0.5, what was it, 66? Yeah. So negative 0.566 v squared. And so v squared, these negatives cancel. And so v squared is 1 point, what was this one? That's the v, 1 point something. And so v is equal to 1.32, and we want the positive. So even though you get some negative signs here and there, everything works out exactly the same, which is, if you think about it intuitively, it kind of is how it has to be. Any questions about that? Uh-huh. Well, I forgot the quiz is upstairs, so I'll be back in 2 minutes and we'll do the quiz.